Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're done with the series on the formation of stars and protostars, so now we're going to learn how low-mass stars like the Sun evolve with time. Stars change during their long lifespans. Their histories reveal how they evolve as they furiously use up their finite but enormous amount of fuel from the moment they're born. Let's look at exactly how they do that. First, one thing to remember is that almost all stars in the sky are really quite boring. Well, boring if you're looking for massive explosions as viewed from Earth. Most of the stars, which can be derided as insanely boring, are so name-called because ultimately they weigh in at less than half the mass of the Sun. They do some really boring stuff that we'll chat about at the end. After the vigor of the Sun, it'll only take one slide to explain them. Thus, 85% of all the stars in the Milky Way can be explained with one slide. After we're done talking about the Sun and these other puny things, we'll go into really more dramatic things such as massive stars that populate the cosmos with heavy elements. But, to be fair, there's an awful lot of research done on these tiny stars because they're so numerous that they might even be havens for exoplanets that might shelter life outside the solar system. So let's begin our journey into stellar evolution with how a star like the Sun changes with time. And so once again, let's start over with the life cycles of stars. This excellent infographic comes from the Chandra Group at Harvard. We see that the mass goes from the low-mass stars at the bottom of the graph to the high-mass stars along the top. We see how stars evolve as time progresses from left to right. Just like in the previous lectures on star birth, we see there's different flavors of protostars. The more massive the protostar, the shorter the time it takes for them to collapse down into a star, and they end up doing something very different. But we're getting ahead of ourselves. We're going to be talking about the bottom three tiers. At the bottom are the brown dwarfs, which don't really seem to do much during their lives. That's not entirely true. So what happens to brown dwarfs? If the protostar is less than 8% of the mass of the Sun, or 0.08 solar masses, this brown dwarf will never initiate fusion in its core. It simply contracts like a protostar under gravitational pressure, releasing heat via the Kelvin-Helmholtz mechanism. We talked at length about this in my lecture on the Sun and in the Starbirth series. Amazingly, a brown dwarf will do that a very long time. It's the closest thing to forever for a brown dwarf to do its mellow thing. Brown dwarfs can also be called hot Jupiters, and there are a large number of massive exoplanets that have been found around other stars that are basically in the in-between zone of a planet and a star. These non-stellar objects make up a huge number of the objects in the Milky Way. Next, second level, we have the red dwarfs, which will eventually become white dwarfs. These live between 8% and 25% of the mass of the Sun. They do fusion in their core, with the least massive doing so just barely. But these just barely stars make up between 75 and 80% of all the stars in the Milky Way. We don't see them in the sky without telescopes because they're far too dim. Next is the primary subject of this lecture. Looking at the third tier, the protostar becomes a sun-like star and then becomes a red giant, and its closing epochs forms a planetary nebula, and finally a white dwarf. We'll talk about some of the other stuff up above next time. We see that stars have cycles of birth, youth, middle age, decline, and death. So the source of life of nearly all stars is hydrogen fusion in their cores. Every star that you see in the night sky, and most you don't, is fusing hydrogen into helium in its core. However, many of the visibly brighter stars, such as Betelgeuse and Bellatrix, shine by fusing helium in their cores. But the question that concerns us today is what happens when a star's hydrogen is used up and converted into helium? Then what happens to the star after all this helium is created? Well, for stars like the Sun, the core is too cool to ignite helium fusion. And by hot, we mean, of course, that the helium nuclei in the core are not moving fast enough to have a decent chance of overcoming the Coulomb barrier and therefore quantum tunneling into close enough proximity to fuse. This all means that an inert helium core is slowly building up in the center of the Sun. The main sequence lifespan, which says the same thing as the length of time a star is burning hydrogen, is determined by how much hydrogen is available to fuse in the core. Throughout this chat, I'll loosely conflate the word burning with fusing. The hydrogen fusion or fusion bursting lifetime of a main sequence star like the Sun will last about 10 billion years. Such stars are about one solar mass. The little M circle dot means that is the unit of a solar mass. But if the star is just barely clocking in at 1/10 of the mass of the Sun, then such a star can live up to about 10 trillion or 10 to the 13th years. This is an incredibly long time. The universe itself is only about 13.7 billion years old, which means that literally zero of all the stars in the 0.08 to about half solar mass have run out of hydrogen in their cores. Further, these are all red dwarfs. They are the dimmest and most common stars of all. So the evolutionary cycle of the Sun follows the graphic across the top. For about 10 or 11 billion years, the Sun is a main sequence star. Then for about 1.25 billion years, it's a red giant, where it grows to be roughly the size of Earth's or Mars's orbit. Then it becomes a horizontal branch red giant star for about 100 million years, in which it's stably burning helium. As it runs out of helium, it rises in luminosity to become an asymptotic giant branch star for about 20 million years. At this point, the helium has run out and it sputters like a car with an empty tank and pulses itself apart over about 500,000 years, with the outer envelope all becoming a planetary nebula, which dissipates away after about 10,000 years. At the end of this lifespan, it will be a white dwarf. This white dwarf will only have about half the Sun's original mass. All the rest will go out into space and enrich the interstellar medium with carbon and nitrogen and oxygen and, of course, hydrogen and helium. Right now, the Sun is about 4.5 billion years into its main sequence life of approximately 11 billion years. Amazingly, we know this because of the ages of carbonaceous meteorites with chondrules and calcium aluminum inclusions that date them at 4.567 billion years old. CAIs are 30 million years older than the Earth and about 140 million years older than the oldest rocks known on Earth. The Earth, Sun, and all the planets form from the same nebula, and such meteorites solidified directly from that nebula and live far enough from the Sun to never melt. Anyway, let's look at the age of the Sun. In the center of the Sun right now, the core is burning hydrogen. This is the fusion of hydrogen into helium via the proton-proton chain process. This is possible because it's roughly 15 million Kelvin in the core. If it was a little hotter, perhaps 18 million Kelvin, then the Sun would be burning hydrogen through the CNO cycle. As it stands, the Sun only gets about 2% of its energy from the CNO cycle. I discussed this at length in my video about what's going on inside the Sun's core. Stars like the Sun will do this for about 11 billion years. The current structure of the Sun at 4.567 billion years old, it has an inert helium core down in the center. This helium is the hot ember of the hydrogen fusion that's already occurred. As hydrogen burns to helium, it sinks to the center and doesn't participate in anything at all. In fact, it's getting more and more compressed as time goes on, growing in its degeneracy. The core is completely composed of helium. Surrounding this inert core is a hydrogen burning zone that's still part of the core. This energy transport mechanism of the core region is purely radiative, which I've indicated with the reddish zone. The blue fusion core is also radiative support. That zone is where the fusion occurs. This merges pretty smoothly with the convective zone above it, and it's important to note that the Sun's core does not mix with the convective zone. The convection does not go deep enough. What's down in the core stays in the core. Of course, at the top of the convective zone, that's where we see granules and supergranules in the photosphere, as well as all the active regions on the surface, what we call the surface of the Sun. When the star starts to run out of hydrogen, that's when it leaves the main sequence. Before then, during the main sequence life, two things are always in balance. One, there's a gravitational pull that's pulling the star together, which is balanced by the outward pressure due to the heat coming from the center. Remembering our 9th grade chemistry class, if you have an ideal gas that heats up a little bit, then the gas will expand. Once this gas has expanded to accept the additional heat, if it can radiate away this heat, it'll contract again. For a star, the source of this heat is fusion, and a star can expand since it is gaseous and not a solid or liquid. If a star expands due to additional heat from the core, then that relieves the pressure, allowing the core to cool. This in turn means less heat is generated, and this means gravity starts to win and contracts the gas as it cools. Gravity wins until fusion kicks back in with enough energy to expand the gas above the core again. In this way, there's a continual battle between the inward pressure due to a star's self-gravitation and the outward pressure due to the heat provided by the fusion in the core. After a star is settled onto the main sequence after its protostellar phase, this balance is very good. So good, we don't see the Sun pulsing radially. The energy output from the core exactly matches the energy lost to space. We call this balance of energy supplied to energy lost thermodynamic equilibrium. Also, we call the lack of pulsation due to the balancing of outward gas pressure against the self-gravity of the star hydrostatic equilibrium. On the main sequence, these two equilibria hold true. But when the core starts to run out of fuel, then both balances begin to break down and the star leaves the main sequence. Here's a more detailed view of the conditions and timings of the evolution of a one solar mass star, such as the Sun. These numbers come from computer models of the various well-known physics relations pertaining to stars. We can look at the first column, and we see that the main sequence lifetime is easily well over 100 times longer than the post-main sequence phases, particularly when the red giant and subgiant stages are taken together. Since we're looking at the transition between the main sequence and the final state, meaning a white dwarf that eventually cools off to a black dwarf, we see that this shorter epoch will fill the Sun with change. Even though the surface temperature doesn't vary a huge amount during the change, that's not the whole story. We see that the core density steadily rises as the fusion products are compressed in the core. The size of the Sun will also radically change. When it first becomes a red giant, it'll swell to the size of Venus' orbit, and during the asymptotic giant branch phase, it will exceed the Earth's orbit. The glowing planetary nebula itself will expand to nearly a light year, with the central part of the nebula going to Jupiter's orbit. It will end its life as a core about the size of the Earth. As we see from the Stefan-Boltzmann law for stars below, small changes in the surface temperature will lead to big changes in the luminosity. But a real change for the Sun's future luminosity will be the radius change, when, for that short period at the AGB peak, the Sun will be one of the brightest stars within a couple thousand light years, illuminating distant worlds the way red giants Betelgeuse, Antares, and Arcturus do for our night sky. So how do we determine how the Sun evolves? Researchers using computer code create models using the equations of stellar structure that I showed you in my previous lectures on the interior of the Sun. Plug all this into large computers and let it cook for a few hours or days. These large simulations take as inputs the surface parameters of the Sun, such as known mass, observed luminosity, surface composition, and radius, and munge them up to show how things will change as a function of mass fraction inside the Sun. Combining this with the methods of energy transport, such as radiative and convective transport, shows how the Sun retains and loses its energy to space. These simulations then check what happens as fuel is used up in the core. The model is usually run for time slices on the mass fractions. First, you have to solve the entire Sun for given conditions from surface to core and core to surface, then advance each slice in time, specifically the core, to see how the interior conditions change with time. The models take so long to run because one needs to vary the steps in time and radial mass fraction. This dynamic grid modeling is quite computationally intensive. Luckily, today, unlike back when I was in grad school, you can spin up a bunch of nodes on AWS and run it together if you're on a skimpy university budget. Then, this all takes a huge wad of numbers which are the map of the inside of the star, and it shows you how it changes with time. Below are some papers you can look up if you want to go take a peek at some of the published models of the evolution of the Sun. Let's watch the Sun evolve as determined by these huge simulations. Included in these simulations are observational matchups, meaning that there is something in the sky today that has been observed with the characteristics of the Sun that we'll be discussing. I'll be describing one such model to a great extent. 5 billion years ago, the Sun formed from a dense molecular cloud, such as Barnard 68, or other such dark clouds that we've seen, the Bok globules. It took about 50 million years to form from this stellar cocoon, finally reaching the main sequence at about 4.5 billion years ago. This is the ZAMS, or zero-age main sequence, when the Sun first lit onto the main sequence and started burning hydrogen in its core. At this time, it was very different than we see today. It was a little fainter at about 70% of the solar luminosity. It was a little smaller at roughly 9/10 of a solar radius, and a little cooler at 5580 Kelvin rather than 5800 Kelvin. At this point, the zero-age main sequence, when hydrogen initiation occurred, the Sun came to thermal and hydrostatic equilibrium. What we'll show is a sketch of the Hertzsprung-Russell diagram, and on this we'll plot a track that shows how the Sun's temperature and luminosity changes with time. The Sun is currently a middle-aged low-mass star on the main sequence. Its age is well known by meteorites to be 4.567 billion years, or 4.5 times 10 to the ninth years. Its mass today is our standard unit of mass, the solar mass, which is about 1.99 times 10 to the 30th kilograms. We also use the solar radius as a standard unit of measurement. Its radius is about 700,000 kilometers, or 100 Earth radii. That means end-to-end 100 Earths could fit across the sun. Makes you think about the sizes of sunspots, like the ones you're watching in these images from NASA's Solar Dynamics Observatory. The luminosity of the sun is about 4 times 10 to the 26th watts, which is much more than the human race could generate in 1 trillion years. This solar luminosity is also a standard unit we'll see over and over again in this lecture series. The surface temperature is 5,800 Kelvin. Half of its core has been fused into helium, so there's an enormously large inert helium core in the center of the sun today. The sun at this time is in a state of hydrostatic and thermal equilibrium. The energy that's being lost from the photosphere as light is balanced by energy being produced in the core, and the sun's not getting larger or smaller in size. This is the way of the sun for about 10 billion years. During the sun's main sequence life, the hydrogen-burning part of the core fuses hydrogen into helium using the proton-proton chain at a temperature of 15 million Kelvin. Surrounding the core is the convective zone, with a buffer of a shallow radiative zone separating them. While the appearance of the sun by this diagram makes it seem like the mass might be smoothly distributed, half of the mass of the sun is in the core region. That inert helium core will become important very soon. Even while on the main sequence, the composition of the star's core is changing. Eventually, as hydrogen in the core is consumed, the star begins to leave the main sequence. Its evolution from then on depends very much on the mass of the star. The diagrams show the percentage of hydrogen in orange and helium in blue. We see the percent going from bottom to top, 0 to 100, and the radius increasing to the right, with the core on the left and the photosphere on the right. The top panel shows the composition at the ZAMS, the zero-age main sequence. The sun's original composition was inherited from the interstellar medium from which it formed. From the studies of the local interstellar medium, originally it would have had about 71% hydrogen, about 27% helium by mass. The remaining 2% was other elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. But by number, it started off as about 92% hydrogen, about 8% helium, with all the other elements contributing less than 0.1% of the remaining nuclei. The middle panel shows the distribution today. The composition of the photosphere at the right side of the diagram by mass is 74.9% and helium is 23.8%, which means that some of the helium has settled down into the core due to gravity since the sun's birth. We can see that the blue slab of helium in the core has increased from its original 24% to now about 60% of the mass of the core due to fusion. The core is the only region of the sun that produces an appreciable amount of thermal energy through fusion. 99% of the sun's power is generated in that inner 24% of its radius, and almost no fusion occurs beyond 30% of the radius. The convection starts at about 45% of the radius, so the products of the core do not show up in the photosphere during the main sequence life. The bottom panel shows the state of the sun's composition after 10 billion years. The core will have expanded, and the hydrogen will be gone from the core. The blue fraction of helium that has moved away from the central 30% shows something's happened to the location where fusion occurs. It's moved closer to the surface. At this point, the sun will evolve quickly. Now let's look at the future events according to these models. When a sun-like star reaches an age of about 10.9 billion years, and for the sun, that'll be about 6.25 billion years from today, the star's core will have run out of hydrogen. Then, most of the core's volume will have been replaced by an inert helium ash. As a result of the massive weight bearing down on it, this inert helium core will contract and heat up. Even still, it does not ignite helium fusion. To keep the star from collapsing then, the hydrogen burning moves out into a shell around the core. This shell burning has observable results. At the surface of the star, the temperature will drop to about 5,500 Kelvin, and the size will grow to about 1.6 times the radius of the sun, and the luminosity will increase to about 2.25 times the luminosity of the sun. These three parameters are interrelated via the Stefan-Boltzmann law applied to stars. Physically, its luminosity and radius grow because the fusion source is now closer to the surface. The luminosity increase means that there's greater energy production happening in the core due to these extreme internal changes. As we now follow the track of the Sun into the future, we will see how its appearance will change. The time steps will not be the same between each location on the track as we go forward. It'll just be the path it takes. This path denotes all the observable changes that will happen due to the events and changes happening in the core. Every star will make such changes, and we'll see in future lectures how different stars make different tracks. In our current example, in 6 1/3 billion years, the Sun will leave the main sequence, becoming a subgiant star. So what is this shell burning, and why does it increase the luminosity? All right, so as the Sun runs out of hydrogen, there's less fuel in the volume of the star's core where fusion can occur. Also, the volume of fusion-capable core that's not occupied by inert helium is getting smaller. It's this combination that demands that the average kinetic energy of a given hydrogen nucleus, whether it's a proton or deuterium or even a light helium nucleus, all must be higher. This is because the same top pressure, due to all the same overlying material, the components of the proton-proton chain must move faster and faster just to find other components in order to complete the fusion process. Well, it's not like the nuclei are seeking each other at some speed dating session for lonely singles. There's no intent to them. It's just that in order to maintain hydrostatic and thermal equilibrium in the star, the components of fusion don't encounter each other often enough unless they're going faster. So we can equate the average kinetic energy, 1/2 mv squared, resulting from the faster speeds of the nuclei, to the average thermal kinetic energy, 3/2 kBT. We see that the temperature must increase. With an increased temperature comes an overall increase in energy output by the Stefan-Boltzmann law for a black body. Since this will necessarily heat the gas above the hydrogen-burning shell, it will expand, lifting some pressure off the core. The star's radius will grow until the pressure decreases enough to balance the energy output of the core. But a larger star with a higher luminosity all means that the star is getting brighter. The reaction of a star to running out of fuel is therefore to burn brighter and hotter. Now, while the core temperature is increasing, the surface temperature decreases because the star is getting physically larger, better allowing heat to escape. On the HR diagram, it moves up, more luminous, and to the right, cooler. All the while this is happening, the central core is becoming quite important to the star. The innermost 3% of the star's mass fraction must be all at the same temperature. This isothermal core supports all the weight above it. To do so, the density must greatly increase down to the very center. As the hydrogen-burning shell dumps more ash on top of it from above, the mass fraction of the isothermal innermost inert core grows relative to the entire star. The innermost 3% total core depletion of hydrogen with shell burning around it will be the state of the Sun when it's 9.8 billion years old. The weight of all the star will keep pushing down on this isothermal pure helium core for another 1.5 billion years. For these next 1.5 billion years, the Sun is now what's called a subgiant star. It expands radially in size, keeping a near constant luminosity of about 2.2 solar luminosities and inches towards the base of the red giant branch. To do so, it swells in size from 1.6 to 2.25 solar radii, which cools the surface layers from 5,500 Kelvin down to 4,900 Kelvin. This huge growth of the outer layers means that it's not held on as hard by gravity. Therefore, this lateral move across the HR diagram is accompanied by the start of a slow mass loss in the form of a stellar wind. As time progresses and the star increases in size, this wind will pick up steadily. This marks its approach to the base of the red giant branch. It's interesting that the luminosity stays the same given what I just described, but here the mass loss is now a balancing factor. Since the luminosity is not changing, then conditions in the core must be changing in some new way. More helium ash is building up in the isothermal core, but the core is now strongly compressing, and this compression is still mostly according to the ideal gas law, but that will change soon. Importantly, it is this foundation at the core that supports the entire star by increasing the pressure down to the very center without producing any new energy. The volume where the conditions are ripe for hydrogen fusion above the core remain roughly the same. As more nucleons fall into the region from above, the core contracts below as the newly created helium falls. The larger radius arises because the mass loss takes away the inward pressure due to gravity. The stellar wind mass loss is driven by that huge heat output that is coming from this ever-increasing temperature of this shallow fusion layer. Looking again at our equation, a larger radius but with the same luminosity means lower surface temperatures. The end of the road for this arrangement happens when the isothermal core reaches 8% of the mass of the entire Sun. That's where our limit of the additional 1.5 billion years comes from. Now the Sun is 11.4 billion years old and the core can no longer support the weight above it. It now collapses on the Kelvin-Helmholtz timescale. At this point, there is no nuclear fuel, so the only way to provide heat is to collapse and convert that energy into heat then light. The total gravitational energy of the Sun's inert core divided by the luminosity needed to add to the shell burning to keep the Sun from runaway freefall gives us a time. This time is how long the Sun will be able to support itself in this way, which is only about 900 million years. This collapse of the core marks the very beginning of the subgiant phase of the Sun's life. This subgiant phase obviously must end. This constant luminosity, increasing radius, decreasing temperature phase ends about 250 million years later. And it does so when it starts to become a red giant. While the core collapses and compresses the outer layer, the greatly expanded outer envelope decreases in temperature. This allows the increasing creation of what we call a hydrogen minus ion in the envelope, or an H minus ion. This ion is basically a hydrogen atom with a loosely attached second electron. This wacky-sounding ion radically increases the opacity inside the star, and this increase in opacity creates a very deep convection zone inside the star that goes from the surface photosphere all the way down to where the Sun, or any star of its mass, has created a lot of fusion products from the CNO cycle. This convection is so efficient at transferring energy throughout the star that the outer envelope increases in size even more. Deep in the core, the helium core is still collapsing, getting denser, and releasing its gravitational potential energy as heat and light in a desperate attempt to keep the star from collapsing. And as it does so, it's starting to use a new trick, though: electron degeneracy. In order to know what electron degeneracy is, we first have to look at normal gases. Well, what's a normal gas? Of course, it obeys the ideal gas law, shown here with a simple relationship between the pressure, density, and temperature. Now, the Sun and all stars are fully ionized gases, but the ideal gas law is a good approximation for what goes on inside them. This diagram shows the effect of what's called the Pauli exclusion principle. It states that no two particles in a system, fermions here, can have the same 6 quantum numbers of momentum and position. And by fermions, suffice it for now that this includes electrons, protons, and neutrons. Each of these 6 quantum numbers corresponds to a physical location denoted by the canonical x, y, and z directions, and to the momenta in each of these directions. Each momentum is determined by the particle's de Broglie wavelength. In addition to these 6 quantum numbers, fermions get yet another quantum number, spin, which has 2 states, either 1/2 up or 1/2 down. Why exactly it's 1/2 and why it's up and why it's down, that's a different conversation. Suffice it to say that this diagram is a radical simplification of all this, showing only one spatial freedom and one energy state corresponding to the momentum in one direction. We're just looking at the position and the momentum in one physical direction, say x, or perhaps left-right. These are the available quantum states in our super simple model. And we're only going to stare at the quantum states for the electrons. The protons and neutrons have their own boxes. In each box, or quantum state, the arrow up or down indicates that electron's spin. Now, if we really want to do this right, we'd need a 6-dimensional cube to get all of the quantum states in the entire phase space. But as you can see, a normal gas has a pretty good distribution of high and low energy electrons with a mix of ups and downs. There's lots of freedoms for electrons to gain and lose energy, and lots of places to go. Basically, in a normal gas, all the available quantum states far exceed the total number of electrons in the available 6-dimensional phase space. An electron can easily lose a lot of energy, come to a near stop, but it'll likely get bonked by another electron and jump up high again soon. There's just a lot more open slots than there are electrons. So what happens when you take the energy away from a gas? It gets colder and more compressed. Here we see a very, very, very cold fermion gas. As the temperature drops, the lowest energy states start to fill up. Because fermions in the same system cannot be in the same quantum state, that is, some combination of location, momentum, and spin, they begin to stack up. Some of these electrons retain a lot of energy, even though they've lost all they can. This is because there are no available lower energy states. At temperature equals 0, none of the higher energy states are filled, and all of the lowest ones are completely filled. And this is what we mean by a degenerate gas, and it most certainly does not behave at all like an ideal gas. And it's not just as if it's extremely cold. Extraordinary pressure can force the electrons into this degenerate state, but the result is the same. The inherent heat energy that was in the random motions of the previous ideal electron gas has been sucked out of the system. This provides an extremely strong lattice structure which can now provide the support for the stars weight above it. Remember, this is just the electrons. The protons, neutrons, and other fermionic nuclei could, and in the case of stars are, still in a near-ideal gas law state. The heat energy of the electrons was simply sapped into the layers above the core to keep the rest of the star aloft. In sum, a degenerate gas can occur at extremely high densities, and when it does, this new gas law takes over. This is the equation for a degenerate gas. I want you to note a few things. First, the only two macroscopic variables are the pressure on the left and the mass density on the right to the 5/3 power. All the rest are numbers and constants. M sub E is the mass of an electron. M sub H is the mass of a hydrogen atom. Z over A represents the ratio of the atomic number Z to the atomic mass number A of the nuclei in the gas. Importantly, the pressure is now independent of temperature, and increased compression doesn't lead to heating. This means that the objects could, in principle, be very cold but still have enough pressure to maintain a state of hydrostatic equilibrium. The inequality across the bottom shows the crossover point between the normal gas and significant degeneracy. Here, T is the star's core temperature and ρ is the core's density. If this ratio is less than that number, then it's mostly degenerate. Currently in the sun's core is not degenerate since that ratio is about 5,500, but something like the PUP, the white dwarf orbiting Sirius, is. Its value is extremely below the boundary, so it's fully degenerate. As for solar mass stars, when they begin to climb up the RGB, or the red giant branch, their cores contract and cool off and get increasingly dense. Eventually, these cores become fully degenerate gases. In fact, a core such as this actually cools down in the center of the star, getting a temperature inversion from the outer core to the very center, principally due to neutrino losses from deep in the core. Getting back to the exterior view of our star. As the star climbs the red giant branch, the convection zone continues to deepen. As we saw a bit ago, the base of this convection eventually reaches down into the regions where the chemical composition has been modified by nuclear processes. In particular, lithium burns via collisions with protons at relatively cool temperatures, and because of its rather large nuclear cross-section for reactions, this temperature necessary for the reaction is just below the temperature for hydrogen fusion via the proton-proton chain. Therefore, this has been happening as a minor energy source since its time as a protostar, and during this lithium burning, its most abundant isotope, lithium-7, collides with the proton and produces beryllium-8, which then quickly decays to become 2 helium nuclei. In so doing, lithium has become nearly depleted over most of the star's interior. Next, this shell-burning phase of the subgiant and red giant branch phases mean that the mass fraction of helium-3, light helium, over the middle third of the star has also increased a lot. We didn't talk much about the CNO cycle for the Sun, but it's occurring in small quantities, which means that the core would be enhanced with carbon, nitrogen, and oxygen. All this deep fusion transformation stayed in the core region for all of the star's life, but when the surface convection zone reaches deep into this chemically modified region, the processed material becomes mixed with the material above it, and we can observe the changes in the composition of photospheres of red giant stars, compared to their same mass main sequence counterparts. Astronomers have observed that the amount of surface lithium is lower and the helium is more abundant. Additionally, carbon-12 is dragged down and depleted at the surface, and nitrogen-14 is raised up and is more abundant. Astronomers typically look at these as ratios, such as X12 for carbon-12 and X14 for nitrogen-14, which correspond to the relative depths of absorption features for the carbon-12 and nitrogen-14 observed in stellar atmospheres. It is observable ratios like these that demonstrate the transport of materials from the deep interior up to the surface. This change is called the first dredge-up phase. The first here doesn't imply that all stars do the first and then the second and so on. The first here is another astronomerism. It means the dredge-up of these elements to the surface in this process. More massive stars might skip this dredge-up entirely, doing other dredge-ups, which we'll cover later. What's amazing is that nature provides us with this means of directly observing the products of nuclear reactions deep within stellar interiors, and it is these observable changes in the surface composition that provide important tests of the predictions of stellar evolution theory. After 600 million years of climbing the red giant branch, it reaches the tip. For the Sun's future, the photosphere has made a radical transformation. The outer envelope has expanded to over 160 times that of the current radius. That's about 3/4 of an astronomical unit and would engulf the orbit of Venus. Both Mercury and Venus would be inside the Sun, spelling their doom and destruction. The Earth won't be doing any better, and the mass loss from the Sun will be changing its orbit, steadily dragging it in. The surface of the Earth will be completely molten, all the water on Earth will have been gone already for billions of years, and sentient life will have needed to have moved on long ago. The Sun will have grown in luminosity to well over 2,300 times its current luminosity, which would make the gases of Jupiter and Saturn boil away, leaving their strange cores exposed. The corresponding drop in surface temperature to about 3,100 Kelvin means that the Sun will no longer be a golden G25 star, but will now be a garnet-colored M03, matching the colors of Antares and Betelgeuse in the sky. Down in the core, at the tip of the red giant branch, the central temperature and density have become about 10 to the 8th Kelvin and about 7.7 times 10 to the 6th kilograms per cubic meter. This is now high enough that quantum mechanical tunneling through the Coulomb barrier between helium-4 nuclei becomes effective, allowing the triple alpha process to begin. This is a new fusion process for the star. It is the fusion of 3 helium nuclei into carbon. All this helium has accumulated in the core as a result of the proton-proton chain reaction, and the carbon-nitrogen-oxygen, or CNO cycle, is now available for use. The first fusion reaction of 2 helium-4 nuclei produces beryllium-8. Now, beryllium-8 is very unstable and will decay back to smaller nuclei with a half-life of about 8 times 10 to the minus 17th seconds. But if, before it does so, it encounters another alpha particle, it may fuse with it to produce carbon-12. This first reaction is endothermic, meaning it takes energy to do. So in addition to being a huge electrostatic barrier to overcome, there's a need for additional kinetic energy from the nuclei to create that beryllium nucleus. That kinetic energy comes from the high temperature of the nuclei as a gas. This temperature and subsequent thermal motion must be so high as to provide about 92 kiloelectron volts, which is the equivalent of a high-energy X-ray photon. This gas has to be hot. Luckily, the second step, which has to happen fast before the beryllium decays, is exothermic, releasing a high-energy gamma ray. It is this release of energy that is the new fusion source. Because of these conditions for this process, a high Coulomb barrier for the first step, a need for additional energy to create the beryllium nucleus other than just the 2 input parts, and a fast decay rate demanding a fast find of a fusion partner in this hellish do-si-do, all means that this whole process is extremely temperature dependent. The triple alpha fusion reaction rate goes like temperature to the 40th power. That is, if the temperature rises by 10% when it's 100 million Kelvin, then the fusion rate goes up 45 times. If the temperature happens to double to, say, 200 million Kelvin, then the fusion rate goes up 1 trillion times. It also means that if the temperature dips lower than 100 million Kelvin, the process shuts off completely. Triple alpha is a cauldron of chaotic fusion. At this point, an interesting difference arises between the evolution of stars with masses greater than about 1 solar masses and those with masses less than 1.8 solar masses. For stars of the lower mass bracket, as the helium core continues to collapse during evolution up to the tip of the red giant branch, the core becomes increasingly electron degenerate. Furthermore, significant neutrino losses from the star's core before reaching the tip of the red giant branch result in a temperature inversion near the center, cooling it relative to the layers above where the hydrogen shell burning is happening. When the temperature and density become high enough to initiate the triple alpha process, again, this is about 10 to the 8th Kelvin and 10 to the 7th kilograms per cubic meter, respectively, the energy release in such stars is explosive. The ignition of helium burning occurs initially in a shell around the center of the star, but the entire core quickly ignites, blowing away the core's temperature inversion. The luminosity generated by the helium burning core reaches 10 to the 11th solar luminosities, comparable to that of an entire galaxy. While extreme, this tremendous energy release lasts only for a few seconds, and most of the energy never reaches the surface. It's absorbed by the envelope above, perhaps causing a short burst of mass loss from the surface of the star, but in general, this event is hidden from view and has never been seen observationally. This is called the helium flash and occurs only in low-mass stars. It occurs because of the combination of the basically non-existent temperature dependence of electron degeneracy pressure and the extreme temperature dependence of the triple alpha process. The flash's energy must go first into lifting the degeneracy, turning the electrons back into an ideal gas law state. This phase transition takes a lot of energy. Only then can the energy go into thermal and kinetic energy. Once it does, the core then expands, which decreases the density. A lower density then lowers the temperature, which in turn then slows this crazy reaction rate. Now that these stars burn helium, the extra energy stabilizes the core against collapse. In addition, there's still hydrogen burning in a thin shell outside the helium-burning core. This hydrogen-burning shell remains the dominant source of the star's luminosity. The core helium fusion allows the core to expand, and the core's expansion pushes the hydrogen-burning shell above it outward, cooling it and therefore causing the shell's energy output rate to decrease slightly. This energy output results in an abrupt decrease of the star's luminosity as seen from the outside. The lower luminosity allows the envelope to contract and the effective temperature to increase. This process means that the star will descend quickly into a new region of the HR diagram, the horizontal branch. This whole thing happens fast, lasting only about 1 million years. At this point, I want to point out that you can find much of this material in Carroll and Ostley's excellent undergraduate textbook, Introduction to Modern Astrophysics. This book is the standard textbook for all astronomy majors. At this new phase, there is a helium-burning core with a hydrogen-burning shell for both low and intermediate mass stars. Here, the increasing compression of the hydrogen-burning shell eventually causes the shell's energy output and the star's overall energy output to begin to rise again. In this period on the horizontal branch, the star is in a newer, shorter phase of hydrostatic and thermal equilibrium. The radius of the star is about 10 solar radii, and the temperature is much less than the current solar temperature, about 4,700 Kelvin, and the luminosity is about 40 times that of the luminosity of the Sun. With this associated increase in surface temperature that we found from before, the envelope's convection rises towards the surface. Now, a new convective core develops. This convection arises again because of the steep temperature sensitivity of the triple alpha process. These things combine to push the envelope to be hotter at the surface, causing a blueward horizontal evolution along the horizontal branch. At this time, it's the helium-burning analog of the hydrogen-burning main sequence, but with a much shorter timescale. For Sun-like stars, this blueward advancement only lasts about 100 million years, and while it goes on, the star is quickly building up a carbon-oxygen core, which is still too cool to ignite carbon fusion. Now I want to backtrack just a little bit. Let's take a closer look at something that's already happened back in the main sequence lifetimes of stars that are just a bit more massive than the Sun. It's important to note that many Sun-like stars use the CNO cycle instead of the proton-proton chain for nuclear reactions. Now, the Sun only gets about 2% of its energy from the CNO cycle, but in slightly larger stars, about 1.1 solar masses or more, CNO accounts for 50% and then dominates the energy production at all higher masses. Just like the proton-proton chain, the net result is a conversion of 4 protons into 1 helium nucleus with a release of energy in the form of gamma-ray photons, neutrinos, and positrons. This process does not consume carbon-12. It goes in at the top and comes out at the end. We say it acts as a catalyst. And because carbon and nitrogen have 6 and 7 protons respectively, in order to overcome the repulsion of all these positive charges, the protons must be moving very fast. Because the temperature in a fully ionized gas is directly related to the average speed of the particles of the gas, this is why the CNO cycle occurs at higher temperatures than the proton-proton chain. The limiting reaction is the 4th step, where nitrogen-14 captures a proton. This is because nitrogen-14 has a very small cross-section with respect to all the other things in this chain. This means there can be a measurable buildup of nitrogen-14 during the course of this reaction chain. The next phase of the evolution is very similar to the evolution following the exhaustion of the hydrogen-burning core. It starts to turn redward again on the HI diagram until it starts to bend upward along a path referred to as the asymptotic giant branch, or AGB. The AGB is so named because the evolutionary track approaches the line of the red giant branch asymptotically from the left. The AGB can be thought of as the helium-burning shell analog to the hydrogen-burning shell red giant branch. At this point in the evolution, the core temperature of, say, a 5 solar mass star is approximately 2 times 10 to the 8th Kelvin, and its density is on the order of 10 to the 9th kilograms per cubic meter. This means during the early asymptotic giant branch, a star has 2 shell sources. Although the 2 shell sources are depicted, it is the helium-burning shell that dominates the energy output throughout the early asymptotic giant branch. The hydrogen-burning shell has become nearly inactive at this point. Note that the diagram is really not to scale, and to visualize the structure from the hydrogen-burning shell inward, I've had to cartoonify it and greatly enlarge it relative to the surface of the star. The expanding envelope initially absorbs much of this energy produced by the helium-burning shell. As the effective temperature continues to decrease, the convective envelope deepens again. This time it extends down into the chemical discontinuity between the hydrogen-rich outer layer and the helium-rich region above the helium-burning shell. This mixing results in a second dredge-up phase, which increases the helium and nitrogen content of the envelope. This nitrogen comes about from the incomplete CNO cycle I described before. In fact, when running stellar evolution simulations to equilibrium, there's always an excess of nitrogen-14 because of its small interaction cross-section with proton collisions. The enhanced nitrogen-14 has been observed in red giant stars, which confirms the existence of the CNO cycle and again tests these stellar evolution theories. Our Sun-like star is now rapidly climbing the asymptotic giant branch, or the AGB. During this brief 20 million years, its carbon-oxygen core will steadily contract and heat up. Nuclear fusion is only occurring in a helium-burning shell, and above it lies a mostly helium non-burning shell with a thin, nearly dormant hydrogen-burning shell above that. Externally, the Sun-like star swells, becoming cooler and brighter. It will be brighter than its previous ascent up the red giant branch, and it will occur much faster than 20 million years compared to 600 million years. If this were the Sun, then its outer layers would expand to about 85% of an astronomical unit, once again nearly to Earth's orbit. The Earth would no longer be there to greet its increase, having been aerodynamically dragged into its doom during the red giant phase. Now, it's likely Mars's turn to fall inward. Generally, for such stars, the surface temperature drops to about 3200 Kelvin, but the luminosity significantly increases due to the core's incredible heat generated by the helium shell burning. This enhanced luminosity leads to a shorter lifespan in this evolutionary phase because faster burning equals a shorter lifespan. As it reaches the upper portion of the asymptotic giant branch, the quiet hydrogen-burning shell reignites and dominates the star's luminosity source. This time, however, the helium-burning shell is being forced to occupy an ever-narrowing layer of the star's core. It also begins to detonate on and off semi-periodically. These repeating helium shell flashes occur when the hydrogen-burning shell dumps helium ash onto the helium layer below, increasing the mass and forcing it to become slightly degenerate. At some point in this dumping, the temperature at the base of the helium shell increases enough to cause a helium shell flash. This is close to the same process as the helium core flashes of low-mass stars, but without their huge energy output. Each flash drives the hydrogen-burning shell outward, cooling it and temporarily shutting it down. Once the helium shell burning calms down, the hydrogen-burning shell turns back on, and the cycle starts all over again. The time between each pulse depends on the mass of the star. Higher mass stars, around 5 or so solar masses, can do pulses every few thousand years. But low mass stars, down to about 60% of a solar mass, can take hundreds of thousands of years between pulses. Importantly, each pulse is stronger than the previous. The graph that you're looking at comes from a simulation for a star with about 60% of the mass of the Sun, and it comes from a 1982 Astrophysical Journal article written by Iko Ibn, a pioneer for such stellar interior modeling. It details the luminosity as a function of time. This sequence for a low-mass star lasts about 2.5 million years. You can clearly see the effect of the flash radically increasing the luminosity, followed by a sharp drop in luminosity, which are the spikes in the graph. Near the tip of the AGB, the dominant source of the star's energy is coming from the hydrogen-burning shell. But when a helium flash occurs, the hydrogen burning nearly stops. This means, from an outside observer, the star's radius decreases during a flash, as well as its total luminosity, but its effective temperature increases. These shell flashes last longer than the helium core flashes, but not by much, as you can see by the slenderness of the spikes. When they abate, it's because, once again, that energy from the flash went mostly into lifting the electron degeneracy. Once that happens, gravity wins out and the hydrogen-burning shell reaches closer to the core, quickly redominating the total energy output. The star will then return to a new state that's close to its previous surface radius, luminosity, and effective temperature. But now, it's a bit more luminous and a bit lower surface temperature. After each flash, the luminosity starts at a lower point, again dumping helium ash into the growingly degenerate helium-burning shell. This repetition continues throughout the star's life on the upper reaches of the asymptotic giant branch. For stars slightly more massive than the Sun, say 5 or so solar masses, these thermal pulses create yet another deep convection cycle, which brings up carbon-rich material to the surface. This can be seen in the spectra of red giant stars. Notice in this sample spectrum that we're focusing on the visible wavelength bands, which are between 4,000 and 7,000 angstroms. Nearly all the emission is in the red end. This is typical for such carbon stars, where you see the banding absorption features due to numerous and varied carbon molecules, such as silicon carbide, in the star's expanded envelope. Carbon stars have recently become extremely important for cosmology. The tip of the asymptotic giant branch can be completely characterized by these carbon stars, making this part of the HR diagram a good standard candle distance indicator, as long as you have a large enough sample of stars in a distant galaxy. This physical process allowed a recent team, led by Wendy Friedman at the University of Chicago, to publish that the Hubble tension can be resolved by studying these stars using the James Webb Space Telescope's better resolution. But that's for another video. It's important to note that carbon stars are numerically predicted outcome of the stellar interior simulations of stars more massive than the Sun in their autumn years. These star spectra show evidence of stellar nucleosynthesis as predicted by these models. Now, these kinds of stars are very frequently variable stars, meaning they get brighter and dimmer through time. One known group of well-observed variable stars are called LPVs, or long-period variables. These stars are observed regularly by both professional and amateur astronomers. They range in pulsation timings between 3 months and about 2 years. The variable star named Mira, or Omicron Ceti, is one such star. This light curve is provided by the American Association of Variable Star Observers and shows the last 6 years of data. Most of these observations are visually by eye, either with binoculars or through a telescope. Mira can vary up to 7 magnitudes, and remember that a difference of 5 magnitudes is a difference of brightness of 100 times. So this star can vary over 100 times in brightness over about 300 days. Looking at Mira in ultraviolet and visible compared, we see that Mira's space velocity leads to an interesting self-interaction. I've alluded to the mass loss that can occur with these red giant stars, especially the AGB stars, during their thermal pulse phase. Mira's motion combined with the mass loss creates a bow shock. Since this outflow is principally composed of hydrogen, we see the Lyman alpha UV emission due to shock-heated gas. This motion is so fast that the hydrogen gas is ionized, and the emission is due to the recombination of the electron back into a hydrogen atom. Watch my video series on the interaction of atoms and light to learn more about this process. What Mira shows is visual evidence of the result of these thermal pulses. The outer envelope is ejected as a fast wind, and by fast we mean the star will lose about 10 to the minus 4th solar masses per year. That's 1% of 1% of a solar mass. The Earth is about 3 times 10 to the minus 6th solar masses, so such a star will lose about 100 Earth masses of material every year. For a 5 solar mass star, it'll take somewhere between 10 and 30,000 years to slough off everything above the core. For a star like the Sun, this means that it will lose 60% of its original mass out to space in a super wind. This wind will be composed of hydrogen, helium, carbon, nitrogen, lithium, and a lot of other elements that are pretty surprising. This mass loss will happen, as we saw before, in a series of about a dozen or so puffs, where the star's radius radically increases, leading to mass loss, followed by contraction and an even larger puffed-up radius. The last of the thermal pulses blows off what is left of the envelope over the course of a few thousand years. As the last of the envelope comes off, the hot carbon-oxygen core of our now-dead Sun-like star is unveiled. As seen from the outside, the temperature goes from 4,000 Kelvin, as seen in the envelope's gases, to 120,000 Kelvin, the supremely hot laid-bare core. However, the luminosity stays constant at about 3,500 solar luminosities. This incredible temperature of the bare core means that most of its emission is in the hard ultraviolet part of the spectrum, with even some soft X-ray emission for a while. These intense and numerous ultraviolet photons ionize the ejected envelope gas, forming a planetary nebula. For the next 10,000 years, the nebula is continually ionized and heated by this hot central core, blowing it and expanding it away to the space between the stars. The interstellar medium will now be enriched and changed by this infusion of processed material. The overall hydrogen content of the interstellar medium is thus infused with new helium, carbon, and oxygen, and all the other elements that are created in that star, which were dredged up and expelled. Incidentally, they're called planetary nebulae not because they're composed of planets or because one day their elements will go to seed future planetary disks around yet-to-be-born stars. They're so named because of the planet-like round shape of the nebulae, as observed by astronomers through early telescopes. William Herschel seems to be one of the first to coin the term in the 1780s because he thought these nebulae looked like planets. But the most definite use comes from the French astronomer Antoine Darquier de Palapoix in January of 1779. On a cold night, he described the Ring Nebula as being very dim but perfectly outlined. It is as large as Jupiter and resembles a fading planet. Just like so many astronomerisms, we know these nebulae aren't related to planets in a direct way, but the name is stuck out of a deep respect for history and an overriding desire to lightly annoy young astronomy majors and decidedly confuse non-English-speaking astronomers. Let's now take a closer look at some of these planetary nebulae. As we zoom in around the sky, the first thing we'll look at is the Dumbbell Nebula. The Dumbbell Nebula is located in the constellation Vulpecula, and it lives at a distance of about 1,360 light-years. It has the honor of being the first planetary nebula to be discovered by Charles Messier in 1764, and is the 27th object in the catalog that bears his name, which contains a list of things that are not comets as per him. It's easily visible in binoculars, and it has a visual magnitude of between 7 and 8, and it's one of the favorite for amateur astronomers' star parties all over the world. I took this image using iTelescope's T18 scope using 3,000 seconds of stacked exposures in each of the RGB filters. It took only a little bit of simple processing to bring out these stunning colors. Astronomers at the National Autonomous University of Mexico computed its angular rate of expansion to be about 2¼ arc seconds per century. This angular size expansion, combined with the known distance, gives an age for this nebula of about 14,000 years. This would be an upper limit because of the angular orientation effects, but other groups have settled on it being about 10,000 years old. And if you look closely, you'll see the dumbbell contains these knot-like structures. These knots vary in appearance from symmetric objects, which sometimes have tails, to others that are really irregular and tailless. Their formation and the way they move and how they track through time depend intricately on how the star blew itself apart. At the center of the nebula, you can see the bare core, with about half a solar mass of material. The rest of the 4 or 5 solar masses of the star are in this nebula. And there's also a much dimmer component, here not visible, but shows up also as infrared emission. Now we're going to swing over to NGC 6302, also called the Bug Nebula or the Butterfly Nebula. This one is a bipolar planetary nebula in the constellation of Scorpius. It is one of the most complex planetary nebulae ever observed. The spectrum of NGC 6302, the Bug, shows that its central star is one of the hottest objects in the galaxy, with a surface temperature of over 200,000 Kelvin, implying that the star from which it formed was very large. The central star cannot be observed and is surrounded by a really dense disk composed of gas and dust, which you can see in the middle, and it makes it look like a pinched waistline for the nebula. This dense disk seems to have caused the star's outflow to be forced into this hourglass-like shape that you see. Just like many other prominent planetary nebulae, it's filled with ionization. We're in the form of walls and knots, and there's sharp edges to these lobes. And this bug is located approximately 3,400 light-years away, and the super winds from the thermal pulse AGB era, combined with the intense UV emission of the core, have accelerated the wind of material up to 600 kilometers per second. This amazing image was taken by the Hubble Space Telescope after the successful 2009 servicing mission and was a showcase image of that wonderful telescope's upgrade. Next on our tour is the Helix Nebula, which is located in the constellation Aquarius. Discovered around 1824 by Carl Harding, the Helix is one of the closest of all the bright planetary nebulae. The distance was measured by the Gaia mission to be about 650 light-years, well within the easy grasp of this parallax studying telescope. At this distance of 650 light-years, with an angular size of 25 arc-minutes or half a degree, it gives a physical size of about 0.8 parsecs or 2.5 light-years across. With an expansion rate of about 31 kilometers or 30 kilometers per second, you can then make a good determination of its age to be about 11,000 years. Due to its unique appearance, you've probably already seen it or heard it called the Eye of God or the Eye of Sauron. Personally, I've enjoyed The Lord of the Rings since I was little, so I'm leaning towards Sauron staring at us. Again, you can see the core at the center of the nebula. It's worth just pausing for a moment and thinking about the fact that this core is not much bigger than the Earth, but yet its temperature is so high that its luminosity is incredible, and it can ionize all that gas all the way out to about a light-year in every direction. This means that if you traveled in a spaceship within about a light year of this nebula and entered the gaseous wisps, your ship would be steadily ripped apart by the ultraviolet light coming from that core. Another name for my astronomy class is A Million Ways to Die, and this is one of them. Finally, in our tour, we go over to the constellation Lyra and view the Ring Nebula, M57, Messier 57. This is one of the great images by the Hubble Space Telescope. This favorite target for summertime amateur astronomers and early fall school star parties is a really tiny target in a telescope, being only about 1 arc-minute across. That's 25 times smaller in the same eyepiece than the previous Helix Nebula. Even though it's extremely far away, at about 2,600 light-years, or about 800 parsecs, that places it only about 30% farther away than the Helix Nebula, which means it's much smaller than the Helix in a telescope then, not because of the distance, but because it's only been expanding for about 1,600 years. This is a much younger planetary nebula than all the previous 3. And what's fun about observing this nebula with a small telescope is using a special filter called an O3 filter, which looks at the specific wavelength of light that are emitted by strongly ionized oxygen in an extremely tenuous gas. The filter clearly shows the massive presence of oxygen. In this image, the bluish green is the oxygen, the reddish areas come from ionized nitrogen. These elements are commonly created in solar mass range stars as they climb the asymptotic giant branch. Coming back out, I've been talking about the cores of these stars illuminating the surrounding nebula. That core is a carbon-oxygen electron-degenerate gas that is now called a white dwarf. Typical white dwarf temperatures range between 8,000 and 40,000 Kelvin, and their sizes are about the same as our home planet Earth. Again, these nebulae are huge, spanning light years, and this tiny, tiny hot object is so incredibly fiercely hot that it's ionizing all that gas. As part of this ionization, when the freed electrons encounter an ionized atom with a free slot, the electrostatic attraction will grab that electron, and the electron will give up the energy of being captured in the form of light. The frequencies and intensities of the light tell us all about the composition of the star that created that nebula. We now see the star turned inside out, with all the material that was for billions of years trapped in the core now being flung out into space. This then is the final stage of our story of a sun-like star. The nebula has now fully dispersed, and the contracting carbon-oxygen core has become so dense that it is now a fully degenerate electron gas. Again, just like with the helium flashes, the pressure becomes independent of the temperature, so the pressure grows rapidly and soon counteracts gravity. The collapse halts when the radius shrinks to about Earth size, and we call this degenerate core again a white dwarf. For the Sun, deep in its future, the bare core will be about 40% of the mass of the Sun. Remember the luminosity equation, where the luminosity of a star is proportional to the surface area times and the temperature to the 4th power? White dwarfs are incredibly hot, but they're also really small. This means that their luminosity is tiny, and that means they cannot cool off with any great ease. The white dwarf that was the Sun will now begin a long, slow cooling phase that will last for nearly 1 trillion years as it fades away into a long night. But wait, the universe is only 13.8 billion years old. This means that not a single white dwarf that has ever been created has turned into a completely cooled off black dwarf. The universe is simply not old enough for a single white dwarf, or any white dwarfs, to have cooled off even to the temperature of the surface of the Sun. So every white dwarf that's ever been formed in the history of the universe still is a white dwarf and is incredibly hot and still emitting huge amounts of ultraviolet light. To learn more about white dwarf stars, see my lecture video series on that very topic. It's important to now look at an amazing result of all this stellar nucleosynthesis. As I described before, some really surprising elements do come out of low-mass stars dying on the asymptotic giant branch. Elements like strontium, molybdenum, tungsten, and even lead are copiously produced during the late AGB time due to the S-process nucleosynthesis. These elements are created in such stars by the excess abundance of neutrons created by all that carbon burning and oxygen burning. Since neutrons don't carry electric charge, they can easily interact with other nuclei. And if the total flux of neutrons isn't too great, meaning that the nuclei aren't getting hit by the neutrons too frequently, then these heavy nuclei, which are frequently radioactive, have a chance to decay into other nuclei before they absorb another neutron. This is why technetium-99 is seen in the spectra of older red giant stars. There are no stable isotopes in nature of technetium, which you can see lies in the middle of the periodic table. And specifically, Tc99 is the most abundant isotope seen in the atmospheres of thermal pulse AGB stars. And it has a half-life of only 200,000 years. So this dredge-up that we've been talking about brings up truly deep material to the surface from very dense regions, which is then expelled out as part of these planetary nebulae. Most of the carbon and nitrogen and lithium in the universe was made in such dying stars. The carbon that makes up the DNA of your cells was made in some ancient star long since dead over 4.5 billion years ago. Oddly, most of the mercury and lead were also created in this way, as well as a good fraction of the silver and gold in your jewelry. So there's our evolutionary cycle for the Sun. As you can surmise, we will never see an individual star doing all of these phases. Our lives are simply just too short. How we measure all this is a combination of computer models based on all known physics, which must be made to match several things. First, the computer models that span a star's full life must be seen to match observed stars in the sky. The models must also predict roughly how many stars are in each phase of their lives. This means we need to sample huge populations of stars in the sky to see where they fall on the HR diagram. If the model predicts a huge amount of red giants, then the input parameters of the physics and the composition of stars must be tweaked to match the observations. And what exactly are these observations? I've alluded to the Hertzsprung-Russell diagram frequently and showed the evolutionary track of a single star around such a diagram. But the first best place to observe stellar evolution is in a cluster of stars. All of a cluster's stars are roughly the same distance, so their brightnesses can be mapped directly to their luminosities. For this famous double cluster in Perseus, we see a pair of classic galactic or open clusters. In this photo, we see a lot of bluish and whitish stars and only a tiny number of bright red stars. This is reflected in the HR diagram of these clusters. Most of the stars lie along the main sequence, and we see a turn-off point for the stars that are leaving the main sequence to become subgiant and giant stars. A few of the more massive stars have already become red giants. The numerical simulations based on all known physics point to these clusters having an age of about 10 million years. A much older cluster, Messier 80, is about 10 to 12 billion years old. The only stars on the main sequence are those stars with masses much less than that of the Sun. We see a lot of yellow and red stars in this Hubble mosaic. This is again reflected in the HR diagram. We see a lot of red giants and subgiants and a bunch of white dwarfs. In the discussion up until now, we tracked just one star of roughly a solar mass. But a cluster of stars has a huge range of masses. It is the mass difference between the stars that tells us where they are on the HR diagram. The more massive stars evolve faster and leave the main sequence sooner. 10 billion years is a long time, and so we should expect to see a lot of white dwarfs, which we do. It is these HR diagrams of clusters that give us huge amounts of information about the process of stellar evolution, which can then inform us as we wish to simulate the life track of a single star. If we then sum up the contributions of a huge amount of stars to a full population HR diagram, we get this. We're looking at an HR diagram of more than 4 million stars within 5,000 light-years of the Sun. This data is from the 2018 second data release from the European Space Agency's Gaia satellite. This satellite obtained parallax distances for all these stars, so we didn't have to rely on them being in the same cluster as previously. This local galactic neighborhood HR diagram shows the groupings in different regions due to differing masses, chemical makeup, and ages. It is the parallax which then gives us the absolute magnitude on the diagram. As you can see, the vast majority of the stars live in a region that's been named the main sequence, but we also see contributions due to red giants and white dwarfs. The other stages that I talked about are very sparsely represented because those stages are on cosmically short timescales. This HR diagram is the most important tool for all astrophysics, and it relies, amazingly, only on 3 parameters: the brightnesses in 2 filters and their parallactic distance. To learn more about how this comes about and how we actually do this measurement, please watch my video series, Cosmic Calibration: Properties of the Distant Stars. Next, as promised from the very beginning, what about really small mass stars? We define these stars as having less than 40% of the mass of the Sun. These stars, too, will be on the main sequence, or at least get there eventually, burning hydrogen into helium using the proton-proton chain at a cool temperature of 10 to 12 million Kelvin. But their low mass means they cook that fire on just the boundary of fusion, and so will last for nearly 1 trillion years on the main sequence. These stars will never get a degenerate core until the very end, when the entire star has been turned into helium and becomes a helium-only white dwarf. These stars will devour, very slowly, all of their hydrogen because they're fully convective and from the very core to the tip of the surface. These are the slow crock-pot cookers of the universe. Their trillion-year lifetime means that there's not a single M-dwarf-type star that has ever died in the history of the universe. Again, the universe is only 13.8 billion years old, and these stars live to about 1 trillion years, which is 1,000 billion years. Even more interestingly, these stars make up about 70% of all stars in existence. But they're very, very, very faint and very underluminous. When we look out at the night sky, we don't hardly see any of these stars. All of the M-type stars that we see in the sky with either binoculars or a telescope are red giants. These tiny workhorses will be around long after the Milky Way has collided with the Andromeda Galaxy and all the hydrogen clouds in the universe have been used up to create other stars. In the deep, deep future, they will populate a dim universe with barely any stars in the sky. If some future astronomer in some young civilization looks out with some telescope into that dim void without any visible stars and finds a tiny fraction of them, his heresy to his contemporaries may very well exceed that of our Galileo. Well, that about wraps it up for the bottom 3 rungs of the life cycles of stars. I bypassed brown dwarfs because they never initiate nuclear fusion. They just keep collapsing and release their heat via the gravitational Kelvin-Helmholtz mechanism. Next time, we'll talk about the more massive stars. For stars much more massive than the Sun, they end in a far more dramatic way, and they occur in a far rarer number. Yet their explosions and the collisions of their remnants make up all the remaining elements in the universe other than hydrogen and helium. We saw how low-mass stars create many vital elements in their cores, but every other element in the periodic table comes about from these titanic stars and their interactions. Thank you for watching this lecture. I want to give a big shout out to my Patreon supporters and my YouTube members. Their support goes a long way to helping me deliver this content to you. I hope that you'll consider becoming a supporter. In any event, please like this video, share it around, and subscribe to my channel for all the latest updates and releases. Thanks again, and we'll see you next time.